Okay, so let's go back to this. Okay, so the square and multiply algorithm for fast exponentiation. So last time we were talking about RSA. And by the way, you guys have a new assignment on RSA, and it seems like most people have started it, and it's going okay. Let me stop the video a little bit early at the end of class today, and we can talk more about that. So in RSA, you compute ciphertext. So X is the message, E is the public exponent, and you want to compute the ciphertext Y is X to the E. So this usually goes pretty fast, and that's because E is purposefully chosen to be a number that is small. Like 2 to the 16 minus 1 is a common choice. So in binary, this is like a 1 followed by a bunch of zeros, followed by a 1. So I guess there would be like 16 zeros here. So it's big enough to make even small plain texts sort of spin around mod n, but it's small enough that this exponentiation doesn't take a lot of time. And it has a lot of zeros for reasons that we'll see in a second. When you do the square and multiply algorithm, zeros go faster than ones. Okay, so that's fine. But when you try to recover the plain text from the ciphertext, you have to do y to the d mod n. So remember what d is. D is the inverse of e mod phi of n. So the d that comes out here is kind of random. In fact, that's part of the security of RSA is that, you know, d is kind of randomly, it's unpredictable. It could be any number in you know, z phi n star. And there's a huge number of numbers there. This is approximately the same size as n, you know, like you're talking about a number that has like 1,000 zeros, and maybe it has like one less zero than n or something. It's a huge number. So when you go from the ciphertext back to the plain text, you have to do a huge exponentiation. And so there's a lot of interest in making that go fast. And if it doesn't, you know, go at a certain minimal speed, then RSA just wouldn't work. So the naive thing to do would just be x equals y times y times y times y times y times y times y mod n. But then if you think about this, this is just never going to work because d is like approximately as big as n, which is approximately as big as like 2 to the 2048. And so you could just never do that many multiplications. So there must be some better idea. And you guys, I think when you take 204, you talk about exponentiation by squaring. So let's give an example of computing x to the 8. So we'll do it two different ways. So one way is to do x times 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 x. So 1, 2, 3, 4, 1, 2, 3, 4. Okay, so you have to do 8 multiplications to do it that way. So here's another way to do it is to do to compute x and then square it, and you get x squared. And now you can square again, and that gives you x to the 4th. And then you square again, and that gives you x to the 8th. So this way we did 8 multiplications. But this way we just did 1, 2, 3 squares. Okay, so obviously the squaring method was much more efficient. Let's try it with some bigger numbers. I'm going to go to a new page. Is that familiar from Math 204?
Yes.
Okay. So let's now let's do x to the 34th power. So I want to, the first thing you do here is you express 34 in binary. So 34 is equal to 32, and no 16s and no 8s and no 4s, but there is a 2 there, and then no 1s. So in binary, this is the number 1, 0, 0, 0, 1, 0. So in base 2. So the square and multiply algorithm operates by having a binary expansion of the exponent. So you have to do that. And then I'm just going to make I'm going to make a little table here. So here's the exponent in binary. And here's sort of the power of x. And we're going to start, gosh, sometimes with these pads, it's hard to draw a straight line. Okay, that's close enough. So we'll start with just regular x. And so the exponent in binary it's 1, which in binary is also 1. So what happens when you square, what happens to the binary representation of a number when you, when you multiply a binary number by 2, it just adds a 0 on the right. So, if you have, what's a number like 7? 7's binary number is 111. Then if you do 14, then this is 1110. So it just adds a 0 on the right. It's like multiplying times 10, base 10, but by base 2, multiplying by 2 makes a 0 appear on the right. So when you square x, you double the exponent. So if I do x squared here, the binary representation of the exponent is now 1, 0. So it kind of creates a new 0 here. What I'm going to do is I'm just going to try to build this. It's all going to be fun and games. So right now we've got this part. We've got the 1, 0 part. And I'm just going to keep going. So I'll square again. Maybe I'll make a little column here for the operation also. So I squared, and then I squared again. And now I have 1, 0, 0. And so 1, 0, it's still zeros here. So I just keep squaring as long as those are zeros. So I square again, it gives me x to the 8. Now I have 1, 0, 0, 0. Okay. And the next one is a 1, but even though that's a 1, I need to square again just to make a place for it. So I square one more time and I get x to the 16th. And now I have 1, 0, 0, 0, 0. But that one actually should be a 1. So there's a 1 in that place. I want that to actually be a 1. So what happens if I multiply in an x? If I do x times x to the 16th, this is going to be x to the 17th. So what it's going to do when I multiply in an x, that just increases the exponent by 1. And what happens when you increase a binary number by 1, assuming this number is 0, it just changes it to a 1. So I can change this to a 1 just by multiplying in an x. So in this next step, instead of squaring, I multiply. And then I get x to the 17th. And now this becomes 1, 0, 0, 0, 1. And this is looking good. I just need this last 0 and we'll be done. So what's the last thing we do here? Square. And so when you square, it doubles the exponent. This becomes x to the 34th, which is what we wanted. And now the exponent in binary is that. And so you can see that that exactly matches 34 in binary. And so we're done. So that's the square and multiply algorithm. Any questions? You can see, as always, feel free to talk over me. So how many operations did we do here? 1, 2, 3, we did 4 squares and 1 multiply. And so that's a lot better than doing 34 multiplications, right? So the bigger the exponent is, the more efficient this is going to be. So let's do it one more time with an actual number. So let's figure out 5 to the 45th power. Doesn't look too good. 5 to the 45th power mod 11. Okay, so what I'm just going to do this. If you know a lot of number theory, then anybody? Okay.
Number.
Yeah, like the stuff from last time. We talked about a couple theorems last time, like Euler's theorem and Lagrange's theorem.
Oh, I don't think I was here for that.
Yeah, it's recorded if you ever want to go back and watch it. So I'm going to do this kind of a
Gotcha.
dumb way, and then we'll. Do you have an idea, Ray? And then.
Oh no! Oh, I'm still like just taking notes.
Okay. So let's just do it the long way. So again, here's the exponent in binary, and okay, and here I'll write 5 to the x, whatever that is, and here I'll record the operation. So we start out with just regular 5, and so the exponent is always 1 to begin with, and we need to express 45 in binary. So 45 is equal to 1, 0, 1, 1, 0, 1. Try to pick something that had a mix of zeros and ones. Okay, so let's go. First we square to make a space. So this becomes 25, but modulo 11, 25 is just 3. And so now I have 0, 1 here. And now I have to decide what to do. So this is 0, so I just square. And so
you said 0, 1. Did you mean 1, 0, or is that a mistake?
Yeah, God only knows what I'm saying. I tend to write and say different things. Please believe whatever I write. So
okay.
Yeah, now it's 1, 0, 0. Okay.
So now do you multiply?
Exactly. So now is a stage where we multiply. So I multiply in 5. 5 times 9 is 45, but 45 mod 11 is 1. And so that gives me 1, 0, 1. Okay. And now we need to make space for this next thing. So we square, and that gives 1, 0, 1, 0. 1 squared is 1. And this one actually is a 1. So now we multiply, right?
Yep.
Multiply.
Yeah, 2, 5.
Yeah, 1, 1, 1. Yeah, so this becomes 5 again. And
now we square for the 0,
square.
right?
Yeah, so we always square.
So when we need a 0, we square. When we need a 1, we multiply.
Yeah, so you sort of always square to like make the next place, and then if the next place is a 1, then you also multiply. And
so where did 5 come from though? Do you multiply 1 with 5?
5 is the number that we're exponentiating. So when you multiply, that means multiply in a 5. Oh,
you can't multiply with anything else?
No, because we just want the power. We want to know what the power of 5 is. Yeah. I'll move this down so we can still see it. Okay. All right. So that actually is a 0, and so sorry. Okay. What am I doing here? Oh, I have the wrong tool. So we square, and that becomes 25, which again is 3.
3, yeah.
And so now we
square again, right?
Yeah, that's right. 1, 1, 0, 0. And so now we have 9. And this last one is a 1. So we have to do one more multiplication. And so that gives us 1,
Which is
0,
45 again, which is 1.
Exactly. Yes, okay. So what we just showed is that 5 to the 45th is congruent to 1 mod 11. And whenever you do this stuff, it's always good to do a check. So let's come here. So we just do power of 5 to the 45 mod 11, and it's 1. Okay, so that's correct. Right. So the thing that is like impossible that a student could ever get right, but which is true, if you're trying to figure out 5 to the 45 mod 11, think of this in terms of like Euler's theorem, which we did last time. So last time we learned Euler's theorem, which says that a to the phi of n is always 1 mod n if a is in the multiplicative group mod n, meaning it has GCD 1 with n. So 11 is prime, so every element is in Z11 star. And phi of 11 is 11 minus 1, which is 10. And so this is saying that, if we just put it all together here, it's saying that 5 to the 10 is 1 mod 11. So if you think about 5 to the 45, 5 to the 45 is 4 times 10 plus 5. So this is the same thing as 5 to the 10 to the 4 plus 5 to the 5, which is 1. Sorry, this should be congruences. 1 to, yeah, okay. So here's the interesting thing that just happened here. So this is going to be especially hard if you didn't come to the lecture last time. But here is 5 to the 10 shows up there. Oh, you know what? Gibran is right. I'm just wrong. Sorry, this is multiplication.
Oh.
Okay, yeah, duh, sorry, thank you. So this is times. Yeah, so when there's a sum and the exponent, that just becomes multiplication in the base. So I can write this as, maybe I did too many steps here. So this is the same thing as 5 to the 4 times 10 times 5 to the 5. And then from this expression, I factored out the 4.
Oh,
Okay,
okay, I got you.
Okay. And now 5 to the 10 is 1, so this just becomes 1 to the 4th. So this is 5 to the 5. So
I had a question from the previous. Can you go back? Can you scroll up?
Yeah.
Okay. So why didn't you just stop at? I mean, why didn't you stop at 40 the first time we got 45? Like after you multiplied it by 9? Because I'm thinking if you don't know what the binary equivalent is like we did, how would we know when to stop? Because if you could repeat.
Yeah, well, that's a good, so when we do this y to the d, the person who's going to be doing that is the person whose private key is d. So they will know d. And then
Got you.
yeah, so knowing d is not going to be a problem for them.
But otherwise there's no way to, like, for example, just randomly somebody wants to find out what the binary equivalent is. There's no way to know when to stop.
Yeah, so if you only know the public key, then there's no way for you to know anything about D, even what it is mod 2. You know, you cannot get a single bit of information about D.
Professor, one question.
Mm-hmm.
In the part where you make a square the square and the multiplication. That part was based in which? Can you repeat that part?
Which part?
When you are doing the square, the multiplication, then the square.
Yeah, like right here, this part.
Yeah, exactly. From the beginning.
Right there.
Yeah. Why is the square square and then multiplication?
Why? Could you say that again?
Yes. Why in the beginning you use a square,
Okay,
and then
okay.
multiplication?
Yeah. So we're basically processing these bits of the exponent. So every time through we square because we need to make a space for the next spot. And then if it's a 1, then we additionally have to multiply. So every time, we always have to square. So this square here just gives us an extra space. And then it happened that one really was 0. So we just squared again. And that gave us another space. But this one is supposed to be a 1. So then we additionally multiply. And now we're here and we need another space. So the square gives us another space here. And it turns out that is supposed to be a 1. So we additionally multiply. Then we square to make another space, and we get this space. And that space is supposed to be a 0, so we just square again. And we get this one. Now this one is supposed to be a 1, so we additionally multiply. So let me just write out the algorithm here.
Okay.
So the algorithm is, this has to, so this is for computing x to the h mod n. This is just straight from the textbook. So this assumes that you know what h is in binary. So we'll say that h is, the sum is I goes from 0 to t of hi times 2 to the I. And each hi is in 0, 1. So what these h's are, these are just the binary digits of the exponent. So hi is just binary digits of exponent. Okay, all right. And so we initialize this variable r is going to store the result. So we initialize it to be x. And then we come up with a for loop that says for I equals t minus 1 down to 0, r equals r squared mod n. So we square at every stage. But if the current digit of the exponent is 1, then we additionally do a multiplication. So r equals r times h. Oh, sorry, it's not times h, it's times x. There's an error in my notes. Mod n. And that's it. So then return r. So the hardest thing about the whole process is just getting the binary expansion of the exponent. So every time through we square to make a space, and then if we need to put in a 1, then we multiply, and that changes to a 1.
Okay.
Something that is kind of funny here, I hadn't planned on talking about this, so that means it's a terrible idea. Side channel, square and multiply. So there's a side channel attack on RSA. Remember, a side channel attack is like when you have access to the physical machine and you can spy on things like power consumption and stuff like that. So this might be like a diagram of the energy consumption of a processor. Maybe there's a better picture here.
I think you talked about this before too in class.
Yeah, I think probably talked about it in your 171 class.
Yeah. It's supposed to be.
Yeah, so okay, so here it is, beautiful. All right, so this is exactly what I wanted here. So if you can analyze the power of the processor while it's doing exponentiation, you can see when it's doing squares and when it's doing multiplies. And if you can observe this, then you can infer what the bits of D are. So just by looking, because you know that there's a square every time, and then when there's additionally a multiplication, you know that that bit is 1. But if there's just a square, then that bit is 0. So you can look at this power graph and you can just read off the bits of the secret exponent D. So if you have some ability to see the power consumption of the computer that's running the private key, then you can learn the private key.
So you said the what's it called, the light, I think, near on the desktop, the
Yeah,
PC mainframe or something
the
like.
flickering light that reads the hard drive. Yeah, there's all kinds of stuff like that. Like if you go to look at real top secret documents, they put you in a room, and you know, it's like EM protected, and also they have like the glass, any kind of surface, they vibrate it, because just, you know, shining a laser on glass, you can detect like vibrations on the glass that will let you infer what people are saying. And there's all kinds of like, you know, sneaky things like this.
So how do you learn to figure out what the light is saying?
I don't know. You know, I could find that research paper and put a link to it up on Piazza. I mean,
That'd
like
be
in
cool.
yeah.
I think the light means that it's like writing or reading, right?
Yeah, and you might be able to like also figure out what the bits are that are being read or written. So this square and multiply algorithm, there's like one iteration for every bit of the exponent, right? And so the running time of this is just the number of bits in D, which is the same thing as basically the natural log of D, except for a constant, but we don't care about constants. So if D is like approximately 2 to the 2048, like on that order of magnitude, then this will run in about 2048 steps, which is kind of amazing that you can do such big exponentiation so fast. You know, these numbers are just ridiculously huge. You guys have seen them from the your current RSA assignment. If you've looked through there, you can actually look at like the private key of an RSA problem. You have to these exponents are enormous, and the bases are also enormous, but you can do these exponentiations surprisingly quickly. So one thing we should notice here is the number of squarings that we do. Is about t. So here t is the number of bits in the exponent. So this is the running time. So this is t. And the number of multiplications is, well, if you assume that there's about half a chance that a bit is 1, then it's going to be, you know, there's half a chance that you're additionally going to have to do a multiplication every time you do a square. So this is a total of 3 halves t operations. These are operations on big integers. So it's so these integers are like you know, they are also on the order of like t bits long. So if you wanted to try to sort of quantify the total amount of work, this is like the number of arithmetic operations. And each arithmetic operation on a t-bit object takes about t squared time. So sort of like, this is kind of like 3/2 t operations, and then each operation takes about t squared effort. So this is like 3/2 t squared, or t cubed. Here I'm assuming that multiplication is like an n squared algorithm where n is the number of bits, which it's actually not. But it's, you know, just, this is pretty good for back of the envelope. All right. So now I'm gonna talk about a speed up technique called the Chinese remainder theorem. And this is a very old idea. I think this is like thousands of years ago. This is some kind of, it's basically modular algebra where you get a bunch of modular linear equations and then you have to solve the system. So there is a technique for doing this that is in some kind of Chinese documents that are really old. But before we do this, we have to go back to this thing that I was talking about before, that I was explaining very badly about the 5 here. Oops. So down here, we wanted to do 5 to the 45 mod 11. But it turns out that I could have just done 5 to the 45 mod 10, which is 5 to the 5th. So that's much less work. And so here's the sort of the justification for that. Is because Euler's theorem says that this number 11 minus 1, which is 10, that the order of the element divides that, which means that when you raise the element to that power, you get 1. And so if you sort of expand what the exponent is in terms of that, you get some remainder. So this remainder here is just 45 mod 10. And so the other part of it just dies because 5 to the 10th is 1, and you just get left with 5 to the 5. So let me just write that down before we get started with the Chinese remainder theorem as sort of a fact. So we need this. If P is prime, and we want to do a to the some big number m, we can just do a to the m mod p minus 1, and it's the same, mod p. Just to give another example, if I wanted to do 7 to the 138 mod 13, this would be the same thing as, what is 138 mod 13? Let me figure this out really fast. So 138 mod 13 turns out to be equal to 8. Okay, so this is this, oh shoot, I did the wrong thing. What did I do wrong?
Percentage?
It's supposed to be 13 minus 1, which is 12. So it's 6. Okay. Okay. Right. So this is the same thing as 7 to the 6 mod 13, which is clearly a lot less work. So let's just go back to Python there and verify that it's true. Okay. So we have pow 7 to the 138 mod 13, which is 12. And if we do pow 7 to the 6 mod 13, this is also 12. Okay, so that saves you a lot of work, and it's part of what makes the Chinese remainder theorem be a shortcut when you're doing big multiplications. All right, so I'm gonna just explain this, but I'm just gonna give an example. if you look at the Wikipedia article on Chinese remainder theorem, it will blow your mind. So it's much more general than what we need. We just need we need it in the special case where n is equal to the product of two primes, p and q. So we do make this assumption. So we have a number n, and n is equal to p times q, and p times q are both prime. So to give an example, let's say that p is equal to 7 and q is equal to 11. So then n is equal to 77. And let's say that we want to know what 9 to the 58th power is mod 77. Okay. So the Chinese remainder theorem says that instead of doing everything mod 77, you can do it mod p and do it mod q, and then put those two answers together to get the answer. So here let's go into mod 7. So that's mod p. And over here we'll go mod 11. So what is 9 to the 58th power mod 7? So this is a much easier problem. For one thing, what is 9 mod 7?
2.
2. So it becomes 2 to the 58th, which is already much easier. Okay, but more is true because I just care about what 58 is mod 6, because 6 is equal to 7 minus 1. So what is 58 mod 6? 6 goes into 54, so this is the same thing as 2 to the 4th mod 7, which is just 16 mod 7, which is 2.
4? Oh.
Yeah, it's 2, right? Because 7 goes into 14. All right, so let's go over here and do it on the mod 11 side. So we have 9 to the 58th power mod 11. And so 9 stays 9, but you can reduce 58. 58 goes down to what? You look at it, 10 is 11 minus 1. And all that matters is the exponent mod p minus 1. So what is 58 mod 10?
8.
Yeah, 8. So this is the same thing as 9 to the 8th mod 11, which takes a little bit of work to figure out. You do, you know, you can use the square and multiply algorithm. So first you have 9, then you have 9 squared, which is 81, which is 4. And then you square that, and you get 9 to the 4th, which is 16, which is 5. And then you square that, and you get 9 to the 8th, which is 25, which is 3. Okay, so the answer over here is 3. All right. So now you've managed to do that exponentiation mod 7 and also mod 11, and that was pretty easy. And you want to take that answer and go back up to mod 77. So you can do it like this. So you found this 2 here. What does that 2 mean? That 2 means that 9 to the 58th power. Let's just call this x because it's sort of unknown. So let's let x be 9 to the 58th. Yeah, mod 77. Okay. So x is equal to 2 mod 7. So that means x can be written as some number a times 7 plus 2. So this a here is just the number of times that 7 goes evenly into x, whatever x turns out to be. And this 2 here comes from that 2. So, right. So now if we take this number mod 7, then 2 comes out. So that's right. So from what the work that we did over on the other side of the page here, we also know that that x is congruent to 3 mod 11, because we did all that work and we found that that number was 3. So we can put these two facts together. So a times 7 plus 2 is congruent to 3 mod 11. And now we can just, we can solve this equation. So subtract 2 from both sides, and you get a times 7 is congruent to 1 mod 11. And now I need to multiply both sides here by the inverse of 7 mod 11. And that turns out to be 8. So a is congruent to 8 mod 11. Okay, so now in this original equation here, I'll just put 8 in for this a. And then I get x is equal to 8 times 7 plus 2, which is 58. So this is saying that 9 to the 58th is congruent to 8 congruent to 58 mod 77, and that turns out to be the answer. That's true. And I'll come back here to Python and prove it. So 9 to the 58th mod 77 is 58. Okay. So I'm not going to give like a very formal presentation of the Chinese remainder theorem, but this is how you use it sort of on paper. Actually, on CoCalc, I gave you my notes from last semester. So last semester, we had more time because we didn't have the coronavirus. So if I can come back here, like open this tab, which is always hard. Let me show you. My daughter is always saying, let me show you something. So I'll go to slides, and then you have day 17. I just gave it to everyone, and it's all about the Chinese remainder theorem. So here the presentation is like much slower, and it's also a little bit more theoretical. So you can read through this if you want to see more examples. There's also this formula. So I did algebra to go from mod 7 and mod 11 back to mod 77, but there's a formula for going straight there. So this is the kind of formula that a computer would actually use. While we are here, let's look at your most recent homework. I get confused because in crypto, your projects are what I call homeworks in my machine learning class. So in this project, you're supposed to actually look at some RSA exponents that are generated by the OpenSSL library. So I just want to skip down to this part where you do all this, and then you get to see an RSA key. So this is an RSA private key for 2048 bits. So here's the modulus. This is just the modulus in hex. And here's the public exponent, which is 2 to the 16th minus 1, which we've said that it often is. Here's the private exponent, which is d. You can see that d is indeed, ridiculously big. This is the factorization of the modulus into 2 primes. So this is p, and this is q. Now you'll also see these things that are kind of mysterious. So there's exponent 1, exponent 2, and the coefficient. So the exponent 1, let me see if I can annotate this here. So you're trying to figure out what, let's phrase it this way, what is y to the d mod n? So these three fields at the end, these are all for using the Chinese remainder theorem as a speed up. So what exponent 1 is d mod p. And then exponent 2 is d mod q. And the reason that you have those is because when you split this using the Chinese remainder theorem, you want to solve y to the d mod p, but then the only thing that matters is, oh, sorry, made a mistake here. When you do this, the only thing that matters is the exponent mod p minus 1 for the reasons that we've been saying here. And the same thing for q. So they just give you these, and why couldn't they just be computed on the computer? I guess maybe smart cards or limited hardware or who knows, but they just give them there as extra parameters. So you also see that there's this thing at the end, coefficient. So I will I'll scroll down and show you the coefficient in a second. It's not super edifying, because it's just another random number. But the meaning of that coefficient is when you go from from mod p world and mod q world, you'll have some answer for the exponentiation mod p, and you'll have some answer for the exponentiation mod q, and you want to put them back together. The formula that puts them back together requires you to know p inverse mod q. And that is the coefficient. And you can I'll go back to the Chinese remainder theorem worksheet here in a second, and I'll show you what the coefficient, where the coefficient shows up in that formula. So let me clear all the drawings here and get rid of that. Okay, yeah. And then this is just the the encoded version of that same information. So here in the formula that lets you go back, so here's p inverse mod q, and I guess they must be using some formula that only requires you to know one of the two things. So that's just wanted to make that connection. So how much of a speed up is it? So when we did the analysis of the plain old square and multiply algorithm without the Chinese remainder theorem speed up, we said that we had to do 3 squared t operations, and then each operation took about t squared time. And so how does that compare to what we do with the Chinese remainder theorem? So n is about t bits long. So n is roughly t bits. And p and q are approximately t over 2 bits. And q is also approximately t over 2 bits. So when we went down mod p, we had to do the square and multiply algorithm mod p. So that was 3 squared, but now it was t over 2, right? And we had to do the same thing for, so this is the number of ops mod p. And then we had to do 3 squared t over 2 ops mod q. And so if you add these two things together, it's kind of funny. You get exactly 3 halves t again. So this is the number of ops. So the number of operations is the same as the number of operations when you do the regular square and multiply algorithm. But the reason it's an improvement is because now each operation doesn't take t squared, because the numbers that you're multiplying are much smaller. They're half as many bits. And so if you do the whole calculation down here, you get 3 half, sorry, just shouldn't have drawn that. So you get 3 half t operations, but now each operation is t over 2 squared. And so what happens here is that you get 3 halves t cubed over 4, because when you square this 2, it becomes a 4. So people say that the Chinese remainder theorem gives you a 4x speed up. So you know this is 3/2 t cubed. This is 3/2 t cubed over 4. So theoretically, you get a 4 times speed up here. This assumes that multiplication is a t squared operation, which I've always found confusing that they make that assumption here, because I think that multiplication can be done in like t to the 1.4 or something, which makes this a little bit less good. And personally, I've never been able to experimentally achieve a 4 times speed up. If we go back here to the worksheet, so here it is doing it both ways. So if you just do this, which I assume is just the square and multiply algorithm, I don't know for sure. This is 43 milliseconds. And if you do it with the Chinese remainder theorem, it's 19 milliseconds. So that's like that's a 2 times speed up, which is not nothing. Like that's worth doing. I've just never personally been able to achieve the 4 times speed up. Okay. Right. So that's about it for fast exponentiation, I think. Anybody have any questions about fast exponentiation? Okay, so we still have 15 minutes left, so let's go on to the this sort of lingering issue with RSA. So RSA requires big primes, n equals p times q, and you know that both p and q have to be pretty big. They have to be like 2 to the 10^24. So how do we find these huge primes? And are there enough primes? So that's the first question. Are there enough primes? So what do I mean by that? So it's, you know, theoretically possible. What if there were only like 1,000 primes that were less than or equal to 2 to the 10^24 or something? So if that were the case, then everybody would just be reusing these primes all the time and nothing would be very secret. So there have to be sort of like so many primes that nobody knows which one you're using. So that's one thing. So there's this function called, this is kind of confusing. I think Euler gave it this name. This pi of n is the prime counting function. And what it is the number of primes less than or equal to n. So for example, pi of 100, I just did this in Python, so I might be off by 1. But there are 25 primes less than or equal to 100, which is the same thing as less than 100, right? So in the, it was conjectured by Gauss, one of the greatest mathematicians of all time, that pi of n, that the number of primes less than n, was usually about n divided by the natural log of n. So just to compare that with this value, if you do 100 divided by the natural log of 100, this is about equal to 21.7. So it's plausible, like 21.7 is pretty close to 25. And this approximation just gets better and better as you encounter bigger and bigger numbers. So there's this theorem called the prime number theorem, which says that the limit is n goes to infinity of pi of n over n divided by natural log of n is equal to 1. So these are sort of asymptotically equal. And this was a really big pure mathematical accomplishment and at the end of the 19th century, which I'm sure they never thought would have any kind of like application at all. And now it has this very serious military application, namely cryptography. Okay, so now we're talking about things out here, these sort of astronomically big numbers. And So we can ask this question. So there, there's definitely, how many primes are there less than that number? Pi of 2 to the 1024 is going to be 2 to the 1024 divided by its logarithm, which is basically the number of bits. So I'm going to be off by a little bit of a factor here. But this is a gigantic number. So this number is so big, that you divide it by 1,000 and it doesn't even notice. This is like zeros running off the page, kind of huge number still. There's definitely plenty of primes. So how do we find one of those primes? There are actually so many primes that if you just pick a big number at random, the chances are pretty good that it will be a prime. So let's pick a big number at random. What is the probability that it's prime? So the probability that it's prime, let's say that the big number is n. The probability that n is prime is roughly the number of primes less than n divided by the number of numbers less than n.
Somebody's slacking.
Yeah, somebody's listening to a commercial or something.
Caught slipping.
So using the prime number theorem, we can write this as n over natural log of n divided by n, which is 1 over natural log of n. So if you pick a big number at random, the probability that it's prime is like 1 over its log. So if you're talking about numbers near like 2 to the 1024, the probability that a randomly chosen number way out there is prime is like about 1 over 1024 roughly. So if you just pick a big number at random, you've got about a 1 in 1,000 chance of it being prime, which is good enough for us because it turns out you can quickly check whether a number is prime, and you can do it so quickly that a computer can do it 1,000 times really fast. So this is basically how we find our big primes. We just select big numbers at random and then check to see if they're prime. So how do you know if a big number is prime? Because you can't factor it. So if I just look at some huge random integer, we could just make one up, blah, 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 blah. And so on. We wouldn't be able to factor that number if it was this big. That's exactly why we use numbers that big, is because they're too big to factor. That's what gives RSA its security. But you might think that there would be a way to determine whether a big number is prime without factoring it. And it turns out that there is a way. So there are things called fast primality tests. And most of these things are what's called probabilistic. And so the way it works is if the algorithm says n is prime, it might be wrong, but it's almost certainly right. Probably right.
What are the chances?
Yeah, so what are the chances? The chances of it being wrong are like 1 over 2 to the 200 or something like that. So it's basically 0. And if it says that n is composite, then it's definitely right about that.
Mm-hmm. So if it's like a large number, would that make a difference in the chance of it being right or wrong?
It can be as right as you want, because it can, there are certain things that are true of all primes. Like all primes are supposed to respect Fermat's little theorem. So for all primes p, it's supposed to be true that a to the p minus 1 is congruent to 1 mod p. So if you have a number and you want to know whether or not it's prime, one thing you can do, so n, let n be a number, is n prime. The first thing, if I had to do this, the first thing I would do is check whether 2 to the n minus 1 is congruent to 1 mod n. Okay, so
Gotcha.
if this turns out to be false, then what conclusion can I draw?
That it's not prime.
Exactly, it's definitely composite. Okay, and what if it's true?
And it's maybe prime.
Yeah, it's maybe prime. And if n is big, then I don't have to use 2. I can let a be 2, but then I can also check other numbers too, like just check a bunch of them at random. So I can check as many random a's as I want. And every time I check another random a, the chances that we're wrongly concluding that it's prime gets smaller and smaller. So
Gotcha.
by checking more and more a's, we can be more and more certain that this is really true, but we're never 100% true, never 100% confident. There are actually, this is one thing that makes cryptography such a cool class, is because it comes right up to like the modern day in cryptography in a way that in mathematics in a way that other classes don't. You can Google deterministic primality tests. So the first algorithm for determining whether a number is prime that ran in polynomial time was only discovered really recently. So I think it's in 2002. Yeah, in 2002, the first provably unconditional deterministic polynomial time test for primality was invented by these authors. And I think they've got it down to, log n here is the number of bits. So they've got it down to like the number of bits cubed, I guess. So that's getting pretty good. But people still use these probabilistic tests, which we'll talk about. The one that I just explained about checking whether Fermat's little theorem holds, that's called Fermat's primality test. But the problem with Fermat's primality test is that there are these numbers called Carmichael numbers. They're not common, but they exist. And a Carmichael number will pass Fermat's primality test. It has a good chance that it won't definitely pass it if you do enough. But so what is a Carmichael number? A Carmichael number has the property, I'll just use the notation here. B to the n minus 1 is congruent to 1 mod n, just as if n were prime. Not for every b, but for all b and zn star. So in other words, the GCD of b and n has to be equal to 1. But remember, for a lot of numbers, zn star is almost as big as n. So, but this will still, if you get unlucky and you have one of these very rare numbers called a Carmichael number, and you try to use the Fermat test, it could fool you. And just because it's fun to know. The smallest Carmichael number is 560 or 561. It must be 561 because everybody knows 560 is composite. Anyway, yeah, here they are. So 561, blah blah blah. So there's only a few of those. I think there's like Wikipedia says that there's 100,000. There's at most 100,000 of them, less than 10 to the 15th, but. Still, it would be better not to worry about Carmichael numbers. So there's a smarter test. Well, I don't know. Fermat was a pretty smart guy, but there's another test that people use called the Miller-Rabin test, which we don't have time to explain, but that will be where we start on Thursday. Okay. and let me stop the recording now. Oops, stop share.